Good day, gentlemen. We're here to report the third chapter of Compass. The reporters are Junaldo, Dagok, and Dayanan. In this report, the goal of this report is that the students shall be able to compute Compass corrections. We have examples 2 and 3 here. If the variation is 3 degrees east and the deviation is 2 degrees east, calculate the compass error. The solution for this is the compass error is variation plus deviation. The variation is 3 degrees east and the deviation is 2 degrees east. So 3 plus 2, we have 5 degrees east. So if the variation is 4 degrees west and the deviation is 2 degrees east, calculate the compass error. So we have two different directions, east and west. Unlike from the previous example that the direction is the same, we just added the two. However, in this example, we need to subtract the two to get the compass error. And whichever is the greatest value shall be the direction of the compass error. Okay, moving on to examples number 4 and 5. Given if the compass bearing is 0.52 degrees, the variation is 4 degrees west, and the deviation is 1 degree east, calculate the true bearing. So the formula for true bearing is um, compass bearing minus the compass error. So we have here how to get the compass error. As discussed earlier, we will subtract 1 degree east from 4 degree west. So we have here the compass error of 3 degrees west. So 0.52 degrees, the compass bearing, minus the compass error, which is 3 degrees west, we can get the value of the true bearing, which is 0.49 degrees. Next example, if the compass bearing is 0 to 8 degrees and the true bearing is 0 to 5 degrees, find the compass error. The solution for this is we subtract the true bearing from the compass bearing. So 0 to 8 degrees minus true bearing, which is 0 to 5 degrees, we can get the value of 0.003 degrees west, or the compass error.
Alright, so
You will read
now
the
we'll proceed to deviation, the ship specific error, or the yeah. So due to onboard magnetic influences, these are the following. So magnetic items, items to which magnets are attracted, wires carrying DC electronic current. So it also reduces effects as much as possible. It keeps compass away from influences, twists nearby DC wire pairs, and usually it can eliminate them all. Also, in here, as you can see in the image, additive effect of compass errors. So, in here in this slide, measuring deviation. So, by using deviation table or the curve, we can obtain the deviation value of a specific compass course. So, first, you have to know how to do some compass calculations. So, in here for the compensation, deviation often is greater than 10 degrees. So special magnets or the compensators installed in compasses to reduce error. So most compasses come with instructions. It can still have significant deviation errors after compensation. So upon computing compass corrections, it has to be the true heading is 00 degrees, variation in chart 15 degrees west. The magnetic heading 015 degrees, deviation 5 degrees west, and compass course 20 degrees. For the worldwide variation, It has a isogonic chart. It illustrates magnetic variation, as you can see here on the image.
So next we have here swinging shift. Swinging shift process of measuring residual deviation error after compensation, usually determined in 15 degrees minus 30 degrees heading increments, are recorded in form of deviation table. Compass adjuster can provide service or you can do it yourself. So next we have back to measuring deviation for each 15 degrees minus 30 degrees. You need to know exactly what direction your boat is pointed. Compare with compass reading, compute deviation. Key to puzzle is knowing exactly what direction you're headed. There are several ways. Example way to know you're heading in calm water with minimal current, remaining in vicinity of Aton. Record both compass heading and relative bearing every 15 degrees to 30 degrees. Compute deviation for each heading. Measuring relative bearings, we have here mounted parallel to vessel keel with all around view, 0 degrees aligned with the keel, align targets in sight, read relative bearing on scale. We have here a photo of an electronic steering compasses and a feature automated deviation elimination. Next, we have local magnetic disturbances. Compass still seems wrong. In some locations, there are local magnetic disturbances that can affect your compass, often noted on charts. All these sound complex, perhaps, but the best solution is practice, practice, practice. Shipboard compasses. We have the gyro compass has three axes: the spin axis, the torque axis, the precession axis. A centrifugal force of the Earth's rotation acts upon the gyro, the torque and precision axis will react and keep the spin axis oriented to a terrestrial meridian. Shipboard compasses, the gyro compass has several advantages over the magnetic compass. It seeks true or geographic meridian instead of magnetic meridian. It can be used near the Earth's magnetic poles, where the magnetic compass is useless. It is not affected by surrounding material. Its signal can be fed into inertial navigation systems, automatic steering systems, and fire control systems. Being a complicated electronic instrument, the gyro compass has some disadvantage. It requires a constant source of electrical power and is sensitive to power fluctuations. It requires periodic maintenance by qualified technicians. Next, we have shipboard compasses. Methods of determining gyro compass error. Although the gyro compass is a very accurate instrument and normally has a very small error associated with its readings, less than zero point 0.1 degrees to zero point 0.2 degrees. The navigator is required to determine gyro error at least once a day. Gyro compass error, like magnetic compass error, is measured in degrees east or west. And next, we have shipboard compasses. If the gyro compass heading is higher than the actual bearing, the error is west. So we have here the illustration for that. Next is the gyro compass bearing is lower than the actual bearing. The error is east. And that is the end of chapter 3. Thank you.